Welcome you all. So in this lecture we will discuss about Yin reaction, Barton reactions, Hofmann reactions and Shapiro reactions. So these reactions are quite important and is having industrially important reactions. So in this, so if you see, can start from the Yin reaction. So this reaction is also known as Alder-Yin reactions by its discoverer. The discoverer was Kurt Alder, and he discovered this reaction in 1943. It is a chemical reaction between an alkene with allylic hydrogen, which is called, in general, this is called ene. So in this, the name, as you see, is called as ene reaction, and a compound containing a multiple bond, which is called enophile, which is having a compound is having a multiple bond, is called enophile, in order to form a new sigma bond with migration of the ene double bond, and 1,5 hydrogen shift has been also takes place. So the product is substituted alkene with the double bond shifted to the allylic position. So if we see here, for the example, if we take the example of this, so we can understand here how does this reaction is being proceeded. So if you see here, if you can remember these things, like alkene with an allylic hydrogen, which is alkene is like this ethylene molecule, C double bond CS2 double bond CS2. So, and you can also see the multiple bond, which is having the multiple bond. So in reactions, carbon, these can be alkene, alkyne, ene can be, you have to see here, ene can be alkene, it could be alkene, it could be alkyne, it could be allene, arenes, carbon heteroatoms compound as well, like carbon double bond O. So these are the ene. And enophiles, if you see the enophiles, so the enophiles can be here, you have to see, once you will look at here. So having a containing multiple, can have a multiple double bond in order to form a new sigma bond. So here if you see this kind of reaction, so this alkene is reacting with this, and here if you see, this is the migration, or this hydrogen is going to be attached here. So if you see here, this double bond is shifting here, like here this will shift over here, and this double bond is forming a sigma bond. So this here, it is a sigma bond is formation is being taking place, and this is this double bond is making a bond with this hydrogen, which is this is broken up from here. So the here if you see, this is making the sigma bond. So here, as per, this is the sigma bond with the migration of 1,5 hydrogen shift. So overall if you see 1 2 3 4 5, so this is the shift from this 1 position to 5 position, so it is also called at 1,5 shift. It's a very simple reaction if you see, and many more reaction can be taken up to understand this. So in reaction, this is the transformation is a group transfer. It is a pericyclic reaction. It means the bond breaking and bond formation takes place simultaneously, and therefore usually requires high activated substrate and or high temperature, because the both things, because these are a concerted reactions, and concerted reactions mean in which the bond broken and formation takes place simultaneously. So the reaction is compatible with the wide variety of functional group that can be appended to the ene and enophile moieties, and many useful Lewis acid catalyzed in reaction have been also developed, which can afford high yield and selectivities and significantly lower temperature, and making the in reaction a useful carbon-carbon forming tool for the synthesis of complex molecule and natural products. So this is the wide application as far as the application of these reactions. So this is just being synthesized by the researchers. So on their name, these reaction has been named in their name. And however, after the synthesis of these compounds is having a very wide applications for natural product synthesis and complex molecule synthesis, which is having various application as far as comes to their application. This is quite important. So here, if we see there schematically, so here you can see the transition state is being formed, and HOMO and LUMO of enophile. Here the LUMO enophiles with lowest unoccupied molecular orbitals is having the reaction with the highest occupied molecular orbitals of ene, and then finally after the 1,5 shift of hydrogen is making this this rearranged products. So in reaction is having many more examples. So here you can see the reactions like this kind of reaction, which is having the methyl groups here. So carbon double bond carbon, and this can react with here in this compound at around this having the conditions methanol and at different at one equivalent of this. So these are the number of reaction can be seen, can be used to visualize this, and many more reaction can be seen during the synthesis. So now coming to the another name reaction or another type of reaction, which is called Barton reaction. So this is again the on the basis of the name of the scientist who got the Nobel Prize in he discovered in 1960 the name of the scientist Sir Gerard Barton, and in 1969 he got the Nobel Prize. So these are having a very exceptional use of these reactions. So for his excellent work to make this reaction, they got the Nobel Prize. So here the Barton reaction is also known as the Barton nitride ester reaction. Is a photochemical reaction that involves the photolysis of an alkyl nitride to form a delta nitroso alcohol. So the Barton reaction involves a homolytic, it is homolytic fission between, here you can see R is the long chain carbon, it could be 4 or 5 membered carbon, straight chain carbon, and NO. So here this the breaking of photolysis is being takes place between these two heteroatoms cleavage, followed by delta hydrogen abstraction. So alpha, beta, gamma and delta position if you see in this reaction. So this is what is being stated here. The free radical recombination and tautomerization to form an oxygen. Selectivity for the delta hydrogen is a result of the conformation of the six-membered radical intermediate. So this proceeded with the six-membered ring, because here this the formation of the six-membered rings takes place and it goes through the intermediate steps. So this type of intermediate will be formed out. So often the site of the hydrogen atom abstraction can be easily predicted. This allows the regio and stereoselective introduction of the functionality into complicated molecules with high yield due to its then unique ability to derivatize otherwise inert substrate. Barton used this reaction extensively in 1960s to create a number of unnatural steroid analogs. So this is again, if you see as far as the application of this reaction is for the alkaloid synthesis, and among them the steroids, he tried to synthesize in the lab different kind of steroids, and these are the boosters, they enhance the physical activity at the higher state. So these steroids and higher alkaloid series compounds he has synthesized. So if you look at the mechanism, So this is the direction specific reaction, regioselective reaction. So the Barton reaction commences with a photochemically induced cleavage. So here if you see this, the cleavage of the O-NO bond, and this makes the radical, and photolysis reaction is this. So photolytically it broken up in this radical form, and radical formation has been takes place. So during these are the intermediary steps, and finally this product is being formed. So here if you see this reaction further, so this is going to be rearranged in that way. So here you can see this is the same time, this hydrogen is, this is half hook arrow. So this is going to be react with this one electron, this the one electron of this carbon hydrogen bond is going to be breaking up. So further this is being picked up by this proton. So this NO group is being shifted from this ONO2 and the another carbon, which is the far away from the delta position of this carbon, alpha, beta, gamma and delta position. Now further, this is the delta hydrogen abstraction. You can see here. So this hydrogen atom is being abstracted from this hydrogen. You have to see here, and this hydrogen is being here you can see it is in a very easy way. So this hydrogen is being abstracted, and then you can see how does here you can see this is hydrogen is abstracted from this alpha hydrogen, and this is rearranging. After that it is making NO and RH here. So this hydrogen can rearrange over here, and this double bond will shift here. So this double bond is going to be shift in between the nitrogen and carbon, and which can be seen from here. So there are a number of rearrangement can be seen, can be possible during the course of the reactions. So here the carbon centered radical can be intercepted by other radical source such as iodine or acrylonitrile. So other compounds or other radicals can intercept the radicals if you want to intercept that. So the first instance result in the delta hydrogen being replaced with iodine, then subsequent cyclization to a tetrahydrofuran by the SN2 reaction. The second example result in the chain elongation product with the oxime form carbon unit, 2 carbon unit further from the oxygen than the normal one. So by this way you can see these mechanism has been proceeded and having the great importance in the higher alkaloid synthesis. Alkaloid among them, like the most important application of this reaction is steroid synthesis. So now coming to the another reaction which is Hofmann Loffler reaction. So here is in a very important reaction. It is also called Hofmann Loffler reaction or Hofmann Loffler Freytag reactions, or you can say Loffler Hofmann reaction. So like these are the names by which this reaction is being generally known, and is an obviously is an organic reaction in which a cyclic amine to pyrrolidine, or in some cases piperidine, is generated by thermal or photochemical decomposition of an halogenated amine. Here this is being indicated by this first this compound N halogenated. This is the halogen is N halogenated amines. So this can be can be decomposition, can be takes place with the help of either thermally, or you can use the UV or photolysis or photolite. In the presence of a strong base has been taken up, so you have to take the strong base or strong also you have to take the strong acid like sulfuric acid can be also taken up, or concentrated fluoroacetic acid can be also taken up. The Hofmann Loffler Freytag reaction proceed by an intermolecular hydrogen atom transfer to a nitrogen center radical and is an example of a remote intermolecular free radical CH functionalization. So here this is the final product, which is the cyclic amine has been formed. Here this N could be 1, 2 or like that. So here X could be halogens, R1 is alkyl or aryl hydrogen, or this is again R2 could be also alkyl, acyl or hydrogen. So this way this reaction can be simplified way, it can be represented by this way. So now the important things is how does this mechanism has been taking place. So we can see here after this the mechanism can be understand in three two major steps. One is initiation step. So here you can see this is initiating the reaction with the proton. It is getting to be protonated, and after thermally or by the photochemically this is going to be formed a reactions. This is going to be changed in another form. So homolytic cleavage gives you this radicals here, and this is after the rearrangement, or this is just rearrange themselves and makes this intermediate in the initiation step after the propagation steps. So this is propagated further. 1,5 hydrogen abstraction has been takes place here. So this makes a alkyl radicals. So this alkyl radicals is getting to be getting to react with another molecule of this intermediate, and this is forming this compound is forming the another intermediate is having the positively charged, and again another one compound which is also. So finally this base is react with uptake the hydrogen from this overall substrate molecule, and after the removal of the halogen from the this, so it makes a cyclic and alkyl ring compound. It could be 5-membered or higher membered ring. So this is formed at the end as you have seen in a previous slide. So this is the product formation is being takes place in this reaction. So now it is also very important. It is generally accepted that the first step in the Hofmann Loffler Freytag reaction conducted in acidic medium is the protonation of the N-halogenated amine and to form the corresponding N-halogenated ammonium salt. And in case of thermal or chemical reaction of the free radical chain reaction, the N-halogenated ammonium salt undergoes homolytic cleavage of nitrogen halogen bond to generate the nitrogen centered radical cation. So in contrast, it has been argued that the UV light catalyzed initiation involves the free form of N-haloamines and a rapid protonation of the newly generated neutral nitrogen radicals which is formed. So intermolecular 1,5 hydrogen atom transfer produces carbon centered radical, which subsequently abstract a hydrogen atom from the N halogenated ammonium salt. So by this way this reaction. Now we can see the reaction mechanism of Shapiro reaction. And Shapiro reaction, it is also known as tosyl hydrazone decomposition, is an organic reaction in which a ketone or aldehyde is converted to an alkene through an intermediate hydrazone in the presence of two equivalent of organolithium reagent. The reaction was discovered by Robert H. Shapiro in 1967. The Shapiro reaction was used in the Nicolau Taxol total synthesis. This reaction is very similar to Bumford-Stevens reaction, which also involves the basic decomposition of tosyl hydrazone. So this is a Taxol is a compound extracted from the plant. So this is having to synthesize by this reaction. So here if you see this reaction, so uh, base butyl lithium and butyl lithium, it is reacted with this, so it gives the tosyl hydrazone has been decomposed to this compound alkene, substituted lithium alkene here. This hydrazone, intermediate hydrazone, in the presence of two equivalent of organolithium compound, this hydrazone is especially two equivalent of organolithium reagents, and it has been taken up, and then this makes the compound. So in this in this reaction, the actual Shapiro reaction is a ketone or an aldehyde is reacted with para-toluene sulfonyl hydroxides to form a para-toluene sulfonyl hydrazone or tosyl hydrazone, which is a hydrazone. So two equivalent of strong base such as N-butyl lithium abstract the proton from the hydrazone, followed by the less acidic proton alpha to the hydrazone carbon, forming a carbanion. The carbanion then undergoes an elimination reaction, producing a carbon-carbon double bonded, ejecting the tosyl anion, forming a diazonium anion. This diazonium anion is then lost as a molecular nitrogen, resulting in a vinyl lithium species, which can then be related with the various electrophiles, including simple neutralization with water or an acid. So this overall steps has been gone once we see the Shapiro reaction. So this is the final product which is being formed after the that is formed at the end of the reactions. So can be seen here with the Shapiro reactions. So the possible questions which can be asked after the overall discussion is named reactions in which the starting material can be or substrate can be given. So like the question could be asked like complete the following reaction. So the substrate will be given, and the reagents can be given, or the condition which is being essential to proceed the reaction, and you have to give the mechanism for that particular reaction. So similarly, complete the mechanism of the reaction. So these kind of reactions can be given for their completion as a mechanism at the end. So this overall materials presented in this lecture has been taken from the various books and internet websites. So this instruction material is for instructional purpose only, and has no commercial use. And also some online content from the different site has been taken up. You can also refer the many more books written here as a reference for further study in more detail. So thank you so much.